Here on planet Earth, we live at the very bottom of an ocean of air. We call that ocean the atmosphere, and like all oceans, it's really deep. In fact, it's a lot deeper than any of the watery oceans that cover the surface of our planet. For ages, people have tried to figure out just how the atmosphere works. They've studied it from on the ground looking up, floated up into it with balloons and looked around. And now, we even study it with satellites high above the Earth looking down. Scientists and explorers have risked their lives to learn more about our atmosphere. So we figured the least we could do was send our own explorer, Brandon, out to seek high adventure on the sea of air.
For ages, explorers and scientists have tried to discover the atmosphere's secrets, using kites, hot air balloons, airplanes, rockets, satellites, and even lasers to probe its mysteries. What they found is that the Earth's atmosphere is a mass of gases and ever-changing clouds. It's also the main ingredient in making weather. As a matter of fact, some scientists call the atmosphere the weather machine.
The word atmosphere comes from the Greek words, meaning ball of air.
So what's the big deal about air? You can't even see it. And if you can't see it, taste it, or smell it, how do you know if it even exists? That's a good question. In the 1st century AD, a guy named Hero was wondering the same thing. He noticed that if you turn a container upside down and put it straight into water, the water can't go into the container. Why? Well, he figured it was because the container was full of air. But if you make a hole in the top, the water rushes in and the air is forced out. So there's your proof. Air really does exist. Okay, once people figured out that there really was such a thing as air, then they started trying to figure out what it was made of.
Of the mix of gases that we call the atmosphere, about 4/5 is a gas called nitrogen. Nitrogen, or N2, is a very stable gas, so it doesn't react much with other atmospheric gases like oxygen and carbon dioxide. Of the mix of gases that we call the atmosphere, about 4/5 is a gas called nitrogen. Nitrogen, or N2, is a very stable gas, so it doesn't react much with other atmospheric gases like oxygen and carbon dioxide. Carbon and oxygen compounds are used by plants, along with water, but nitrogen doesn't play well with others, and that's why most of the atmosphere is nitrogen. The total mass of the air in the atmosphere weighs an estimated 5.5 quadrillion metric tons. That's 55 followed by 14 zeros. Sounds like a lot, doesn't it? Guess again. That's only a millionth of the weight of our actual planet. And it's the Earth's gravity that keeps our thin little atmosphere from floating off into outer space.
But I'm getting ahead of myself. And anyway, I've got to get ready to sail. So let's hook up with Jason, who's been doing a little traveling himself up into the atmosphere to talk to the experts about our sea of air.
Not that line, Odell.
Aye, aye, Captain.
This is NCAR, the National Center for Atmospheric Research here in the Rocky Mountains. No place better to study the atmosphere. Come on, let's go inside. Here at this mile-high site in Boulder, Colorado, the NCAR scientists gather data and make observations using satellites, weather balloons, and research aircraft. Then, they take all that information and bring it back in here and use powerful supercomputers to help them figure out what's going on up there.
Here at NCAR, the National Center for Atmospheric Research, we do a number of interesting things that have to do with weather and climate. We study the sun, we study the atmosphere itself and the motions therein, storms. We study the ocean, and we study the chemistry of the atmosphere and how all these things interact. We have to go where the weather is. For example, if we study thunderstorms, we'll go to a place like Oklahoma. If we want to study tropical squall lines, we'll go to places like the South Pacific or the tropical Atlantic or to the African continent. NCAR scientists study the weather and climate in a lot of different ways. We have aircraft. We have supercomputers. We have the High Altitude Observatory, where they use a lot of data from satellites and telescopes that are in other parts of the world. The aircraft are used for a number of things. For example, we have a radar in the aircraft, so we can fly close to thunderstorms and look at their interior structure. We also have instruments on the aircraft that measure the wind, temperature, moisture, turbulence, and so on. And if the storms aren't too strong, for example, over the ocean, they're not as strong as they are over land typically, we will fly through them. The atmosphere is the weather machine. The atmosphere is a mixture of gases constantly in motion. Those motions get their energy ultimately from the sun, and they take incredibly diverse forms, highs and lows that you see on the weather maps on television, hurricanes that you can see in satellites, tornadoes, thunderstorms, snowstorms. All of these things ultimately go back to the sun, how it heats up the atmosphere on Earth, and how the air moves. We need it for life. We breathe the atmosphere. Plants need the atmosphere. They take up carbon dioxide from the atmosphere. We take up oxygen from the atmosphere, and we couldn't live without it.
Don't go away. The Weather Classroom will be right back.
So I know you're not with me every night here. So every night on Fox 9 at this time,
yes,
we like to turn to Scott and gives a little closer look. Yeah, he teaches us something usually. Actually, for that matter, Scott, a lot of times it's a weather whiz kid who teaches the older folks here something, older.
So what are we going to learn tonight, Scott?
What are we going to learn tonight? Well, some of the basics to weather. What makes nice weather? What makes stormy weather? That's simple, right? Here's the question from Eagle Middle School.
Hi, my name is Jody Gilbertson, and I go to Eagle Middle School. And my weather question is, why is it that high weather pressure is associated with fair winds and clear skies, but low pressure is associated with dark clouds and precipitation?
Great question. So we're talking high pressure and low pressure. She's saying, why is high pressure associated with clear skies and light winds, and low pressure associated with storms and rain? Well, we're going to put it together this way. You have to look at weather as three-dimensional. That's the key here. That was one of the most difficult things when I went to college. When they started talking about the weather in 3 dimensions, I was so used to just staring at weather maps that I'd see in the newspaper here down at the ground. But everything at the ground is occurring by what's happening aloft here. So let's look at the jet stream. This is the jet stream here, and this is high and low pressure here. Now you have to understand the water cycle too. The water cycle is as air rises, it will cool and then condense, because it encounters lower pressure. So the higher air rises, the pressure goes from high pressure to low pressure. You get less pressure, less temperature. It cools and condenses, makes clouds. So wherever there's rising air, we get precipitation. This is what's happening in the jet stream aloft. Here we'll have a convergence zone aloft here. That's when the jet stream winds are coming together. So as you push the air together, it has nowhere else to go. It can't go up, so it has to go down. And so what happens is we have sinking air, and the air sinks, and it sinks clockwise. So it subsides, as we call it, subsidence. As it's sinking, it warms because it encounters the higher pressure near the ground, and that sinking air also causes a big bubble of high pressure to form here. So sinking air near the high pressure warms and dries, and so you don't have any cloud cover out. We had that pretty much during the day today. As the jet stream is going along, it'll encounter an area where it diverges aloft, and so it separates the air here. We can't have a void. We can't make a vacuum of no air, so something has to replace the air right here, and so air comes up from the ground. So what happens is high pressure now has been over here, so that wind comes out of high pressure, it goes into low pressure counterclockwise, it gets to the middle with nowhere else to go, and it rises to fill this void right here. And so near low pressure we have rising air, and rising air will then cool and condense and make clouds and precipitation. So you basically have rising air causing clouds and rain, while sinking air is generally dry as it warms up. And if you look at high pressure, low pressure on the ground at the surface here, you also have wind that forms between the two. And as I mentioned to the kids, if I take a room and we fill it up with air, we seal it off, and we pump a bunch of air pressure inside the room, then we open the door, the air will rush from high pressure to low pressure outside the door, and because the earth is spinning, it goes around clockwise like this. And so we added a little bit extra here, but generally stormy, not stormy. That's what you got to take away from that, Don.
We don't get quizzed on this, do we?
Oh, yeah. Sitting on your desk.
End of the week, my friends. Let's keep him on his toes.
Okay.
Thanks, Scott.
To find out more about nature's great storms, we have to learn more about the air around us. In this shot from space, you can see the moon and the thick blanket of air that surrounds our planet. It's called the atmosphere. It is an ocean of air dozens of kilometers deep. We live at the bottom of the atmosphere, and the amount of air that's above us presses down on us. We're so used to the air pressing down on us that we can't really feel it. But we can measure it with a device called a barometer. A barometer measures the weight of air in much the same way that a bathroom scale can measure your weight. The weight of air is referred to as air pressure, and air pressure is measured in units called millibars. This barometer shows that the air pressure is just under 1,010 millibars. That's how much air is pressing on the barometer and everybody and everything around it. But air pressure doesn't remain the same all the time. If you were to watch the barometer over a period of days, you would find that the amount of air pressure changes. That's because air pressure is influenced by a number of factors, including temperature. Here's why. In this demonstration, 2 blocks of air have been placed on a balance scale. Air, like everything else on Earth, is composed of molecules, shown here as tiny balls. Molecules are so small they are invisible to the naked eye, and they are shown much larger than they really are. These 2 blocks of air have an equal number of molecules, and that's why they weigh the same. But watch what happens when the block on the left is heated up. Its molecules spread out. There are now fewer of them in the same amount of space. The air rises because it weighs less. But when air is chilled, its molecules come closer together. There are now more of them in the same amount of space. The air sinks because it is now heavier. That's why a hot air balloon rises. The air within the balloon is hotter and therefore lighter than the surrounding air. Air pressure helps determine the weather. That's why most weather maps show areas of high and low air pressure. But weather maps have so many lines they can be confusing. So let's simplify one by removing all the lines except the ones that mark high and low air pressure. These lines shown in white. The areas with H's are high pressure areas. The area with an L is a low pressure area. Some of the boundaries between low and high pressure areas, here for example, can be windy. The wind is caused by the movement of air from an area of high air pressure to an area of low air pressure. You can simulate this yourself. When you blow up a balloon, you are actually increasing the air pressure within the balloon. The balloon now has higher air pressure than the air surrounding it. When you allow the air to escape, it creates wind, caused by the movement of air from a high to a low pressure area. Highs and lows are often associated with fronts. The red symbol represents a warm front. It's called that because it is a place where warm air is moving into and replacing cold air. The blue symbol represents a cold front. This is an area where cold air is moving into and replacing warm air. We've already seen that air's ability to rise is just one of its important properties. Another important property is its capacity to hold moisture. Just as a barometer measures the weight of air, an instrument called a hygrometer measures its moisture content. Air can be either dry or moist. You can't always see the moisture. It becomes visible only when conditions are just right. For example, during the formation of clouds or fog. Clouds and fog consist of water vapor that has condensed into tiny drops.
It's like this. Air pressure is always pushing on us from all sides. About 15 pounds of pressure for every square inch. But at the same time, our bodies push back against the air pressure with equal force. So it balances out and we don't get crushed.
I wish I could see all this.
Well, think of it this way. Picture air molecules near the ground as being packed tightly together by the weight of the air above. This is why air is much denser at sea level. But higher up in the atmosphere, there's a lot less air pushing down from above, so the air molecules are not packed together so tightly. Normally, we don't feel any of this unless the pressure changes suddenly.
You mean like when your ears pop in an airplane?
Exactly. At much greater heights, there is less air weight pressing on you. Your body is reacting to the pressure change.
Scientists use barometers and other tools to study the air pressure, to predict the weather, and to study climates. Knowing how to accurately measure the atmospheric pressure is critical to weather forecasters. When the air pressure is low, it generally means bad weather with storms and precipitation. When the pressure is high, it usually means good weather with clear skies.
Well, we're back here. And as you can tell, there's a special feeling in the audience tonight, and that can mean only one thing. It's time to bring on a great entertainer, a great humanitarian, and my personal friend for over 157 years. Ladies and gentlemen, Bill Nye, the Science Guy. Bill, nice to see you. They love you, Bill. Bill, I see all sorts of exciting things, water, glasses, electronic apparatus. Looks really exciting. What are we going to do tonight?
Well, John, we're going to talk about pressure. We're going to talk about pressure, specifically atmospheric pressure. John, nothing particularly dangerous eye-wise tonight, but you know, it's a great tradition.
What a shame.
It's a great tradition, and so I want you to don the safety glasses.
Safety goggles. Great.
And tonight I chose the red. I think this could be my favorite shirt.
Oh, thank
of
you.
the whole year. I'm not saying. Very cool. John, you look very sharp. Now let's get started right away. Nothing too spectacular. Ordinary deck of cards. I've happened to have selected the Joker. This is a what, John?
It's
Griffin low form. Beaker.
Test tube.
This is a test tube, right. Now, you may do this in a restaurant with a drinking glass, but at Nye Laboratories, we do it, of course, with the test tube. Everyone's familiar with the traditional experiment. Okay, right? Right? You're with me? No applause? That's fine.
That's okay, yeah. You know, that's all right. Only applaud if you feel like it. We're not... Oh, look,
Esther Williams Joker there. And so, okay. Now,
that's great.
John, that's fine. Now, what held the card up?
A little bit of adhesive that you secretly put on the end of the
John,
tube.
no, John. It was atmospheric pressure, John.
That's right. That's what I meant to say.
Pushing up all around, pushing up all around. Now, what causes atmospheric pressure, John?
The atmosphere.
Well, the atmosphere, but more specifically, gravity, John. Gravity's pulling down all the time on the air and creating pressure here at where is this?
Sea level.
Sea level, very close, John. We put a little water in the great cylinder of science.
Okay.
No need to add a joker, but you can. Then we got to swirl the water, John. You know, whenever we have a cylinder of science, we want to create a vapor in here, a little water vapor.
Swirling the cylinder of science.
Cylinder of science. Now, John, we're going to pressurize it as though we were atmospheric pressure. Then we're going to release the pressure as though we were a cloud at high altitude. See, as the air reaches high altitude and expands, it cools, and water vapor comes out of solution. Now, when it comes out of solution, it has to nucleate on dust particles, which we'll get from these matches, and see that little bit of smoke. Now, John, energizing the pump.
Well, Bill, there is no smoke in there, though.
Just the tiniest bit.
But you put the matches out.
In the bottom. But in there, John, is a tiny bit of smoke, creating dust. Dust pervading the cylinder of science.
Okay, well...
And then when we release the pressure on the cylinder of science.
Okay. Let's see.
You ready?
Yeah.
3, 2, 1.
Whoa!
You don't see any cloud until you won't see a cloud until there are dust particles in here. Kind of a subtle, cool thing.
That's very cool, Bill.
So it cools because of gravity, lower pressure, high altitude. Now, John.
Okay.
While we're talking about atmospheric pressure, coming out of this side of the pump is pressure.
Okay.
Pressure. This side is vacuum. Now, John, if we follow the hose
this side
over here, you'll find the vacuum is plumbed, as we say, into the great acrylic plate of science.
Okay.
Now, these pins are for alignment, just to save precious time.
Okay.
Now, can you hear the pump kind of slow down a little bit?
No, did it?
Is
the valve closed and everything?
Let's just check the valve.
Oh, well, yeah, it's sticking.
He's
so
skeptical. Yeah, the valve is closed, John. And indeed, for you gauge buffs, there is
it's closed.
Developing.
That's fine.
Now,
That's fine.
John, what we will do, we will raise the cylinder of science.
Boy,
this will be
Bill,
another cylinder
I
of
don't know
science.
about this.
Up there.
And you're going to get up there and do that?
No, John, I was thinking maybe you'd do it.
Oh.
John,
okay, I'll help me out.
Yeah. Can we get a spotter in here?
Always willing to help the science guy. You know that.
Ed's wearing a science guy shirt. That's very sharp, Ed. The science team.
Oh, boy,
science team.
I don't know about this, Bill.
KXRX or the bond. Now, the extra. Okay. Now, John, we're almost there. And you see, atmospheric pressure is pushing down here, and so great is the surface area of the acrylic plate of science.
Luckily,
that it will support your weight. Quite astounding.
Are we ready to do it?
Well, no, we're yes, we are. Very close, John. Yes. If you will, please
I couldn't
step off the stool of science.
Now,
John, I know you're hanging there.
Okay, Bill.
I will open the valve. Everyone listen and let atmospheric pressure
Bill,
back in.
turn it off now, Bill.
Can you hear the pressure coming back in?
Turn the thing off, Bill.
It's off, John. You're dangling. Don't face the audience. There you go.
Okay.
We're letting pressure back in to prove that the atmosphere is suspending and not those three little
I couldn't do this if I hadn't... That's great. Bill Nye, the science guy.